Hello all. Today we're going to talk about three things that are related but different, but very important when we're dealing with mechanical systems. First thing we'll talk about are fasteners, then we're going to talk about bearings, and then we're going to talk about gears. So fasteners are basically something that holds things together, and the most commonly used fastener in engineering are bolts. And how do we describe bolts? Now, last week I talked a little about different types of bolts and their characteristics and standards for bolts. So we're going to talk now about how do I describe a bolt, and then we'll get back into that standard. So the first thing that we need to know is the length of the bolt that we need and the diameter of the bolt. So those two things are the first things that I look at. Then I look at the threads. There are different types of threads on different bolts. Then the class of bolt, and as we explained last week, that the class of the bolt basically will tell us how strong a bolt is. So depending on its application, I may need a stronger bolt. So I have to know what class it is. And then the final thing that I need to know is whether it's an English or a metric bolt. Most of the things made today are metric, but you will come across stuff made in the United States predominantly that may still have English bolts attached to it. And as I've mentioned in the past, I like working on old cars, and I've come across a lot of older cars that have English fasteners on them, and those actually can be from England also, but predominantly American cars built prior to 1980 have English fasteners on them, and American products built prior to 1980s are mostly English fasteners. So there are a bunch of different types of threads. This is just a small list. And generally, when you look at a bolt, you will see that it either has a coarse or a fine or an extra fine thread. And one of the difficult things in this class this semester, since we are remote, is that I can't actually show you different bolts. And I have a box with different bolts that I pass around so you guys could see how these are different. But the threads become very important because I got to know how it is going to tie into, if I have a nut and a bolt, they have to have the same thread. Or if I have a bolt that is threading into a part, it has to have the same thread. Many years ago, as an engineer, on my personal stuff, I actually replaced the transmission in my car, and I went from a 4-speed transmission to a 5-speed transmission. And at the time, that was my only car, so I wanted to make sure that I could drive that car at the end of the day. And I was super careful in making sure I had everything there that I needed the day that I was going to make the changeover. And everything went well until the last bolt. And the last bolt that I was putting in was actually to hold in the speedometer cable. In the old days, speedometers were gear driven off of the transmission. And as I looked at the specs on my new transmission, I noticed that the bolt was listed as the same size. But what I didn't notice was that my old transmission was a coarse thread and the new transmission was a fine thread. So I actually had to send someone out. Actually, my poor mom, God rest her soul, went out and got me at a hardware store the right bolt so I could get my car back on the road. So it is important to know what threads I have on a bolt. I gave you a PDF last week and also attached a video last week about the different classes of bolts. And this is a chart with SAE bolt designations. And if you have a bolt that's an SAE graded bolt and it has no markings on the head, it's either a grade 1 or grade 2, as is seen in this picture. If it has 3 markings on, and you're skipping one corner, it is a grade 5. If it has 3 marks on it, but they're next to each other, then it's a grade 5.2. And then when I go to a grade 8, it has a marking on each point, and a grade 8.2 has 8 markings, but they're not on each point, they're closer together. And this becomes an important thing to know when I'm looking at it, because you'll see that the material is different, but the strength is also different. So whereas a grade 8, looking at this chart, has a tensile strength of 150,000 pounds per square inch, a grade 1 is only 60,000 pounds per square inch. So there are areas that I would want to use a grade 8 bolt, depending on what the load is on that bolt and you know, how fast it rotates. I will tell you that there is a difference in price, and it is important. And many years ago, when I was soon after I graduated from college, there was a case out in Long Island at an airport where a company that was servicing the airplanes bought bolts and they were mismarked. So somebody marked bolts improperly. And these bolts were being used for maintaining airplanes. And I will tell you that that is a critical thing, because you don't want anything going wrong while the plane is in the air. You don't want something to shear, a bolt to shear off while the plane is in the air. And the company that sold the mismarked bolts ended up having to pay for every single one of the planes that the hardware that was mismarked went on, to come back in and have all of the bolts replaced. And it ended up costing them a lot of money. But again, it was a safety hazard in that, and you cannot let that go by. You know, it is a serious thing to make sure I have the right type of bolts. You know, I'm sure everyone here has had some application where you just can't afford to have that fail, right? What if it's the bolt holding on your seatbelt in your car, right? You want that to fail when you get into a crash because they used the wrong grade of bolt? I don't think so. So that is the kind of stuff we have to look at, make sure we're using the right size and the right grade. My first engineering job as a summer intern, one of the responsibilities I actually had was to actually figure out the load on bolts on a ship for the Navy and determine what grade of bolt we had to use. You know, so again, it's not a light matter. So I'm gonna just read this through and then we'll try to describe it. But basically what this says is, you have the drawing on the left and you see that it says a thread is a continuous helical ridge formed on the inside nut or outside screw of a cylinder. The ridge is called the crest. Between each crest is a space called the root. Threads are set at an angle to the axis of the bolt or nut. This slope is called the helix angle. The angle must be sloped either to the right for right-hand threaded screws or the left for left-hand threaded screws. The thread forms a V shape between the crest. The angle of this V is called the thread angle. So on the chart a few pages ago, when we talked about the threads, one of the things, the way to describe it instead of a fine or a coarse thread, is by the pitch, right? So the pitch is basically, as it is in here, it's the space between two of the ridges, right? And to the crest, I should say, right? And so that is the pitch. One thing that this slide talks about that people are not aware of always is that there are right hand and left hand threaded screws. So very commonly we think of right hand threaded screws, but we have to be careful because there are also left hand threaded screws. So in this slide, I actually have two pictures that are of the same part, but one is left hand threaded and the other is right hand threaded, right? So the difference is, and if you look at it, you could see if I turn the right hand threaded screw clockwise, it is going to tighten. If I turn the left-handed screw clockwise, it'll loosen. So to tighten the left hand screw, I have to go counterclockwise, right? And I mentioned that this is the same part, and I actually, in my box that I talked about earlier, I actually have these parts in there so that I could show you by passing them around, and you could see, hey, the one is threaded differently than the other. And this is a part that everyone in this class has probably seen and never even thought about. And to this day, they still have them as left and right-handed threads on either side. That picture is actually the spindle of a bicycle pedal. The right-hand side of a bicycle has a right-handed screw, and the left-handed side of the bicycle has a left-handed screw. And that is done so that as you are pedaling forward, you tend to tighten the pedal in the crank. And so it won't loosen as you're pedaling it. And I've seen many a person who didn't realize that and tries to turn to loosen, take a pedal off on the left-hand side and is going the wrong way and ends up breaking the crank or breaking the pedal. So be aware that there are parts out there. In the 60s, Chrysler actually had different sides of the car, the lug nuts to be threaded differently for the same reason, so that the tires will tend to stay tight. They ended up recalling all of those cars and changing the studs and making them all right-hand threaded because people do not tend to read their owner's manual, and if they had a flat tire, they were either snapping the stud or breaking their wrench and with the wheel stuck on there. So they ended up having to recall all of those. But I do know that to this day, large trucks still have different threaded lug nuts on different sides of the truck. So we talked about fasteners, and I said, bolts are very important because, it's one of the ways we hold things together. But the next three things that are going to be talked about here, welding, brazing, and soldering, are also a method of holding parts together, right? I don't know if anyone in this class has done any of these. In most of the times when I ask, people have done soldering, right? Soldering is commonly used for joining wires when you're doing electrical work or joining parts. Some people have done welding. Most people in my classes have not done brazing. I actually had one student who had done brazing at one point. So, but all three of these are methods used for joining metal. I'm going to be talking about metal today, but I will say nowadays you will also see someone describing joining plastic as welding. That's not what we're going to talk about today in this class, but it is a term that is used to join plastic. And when we look at how a weld is made, it kind of makes sense that you could use that term for plastic because a welded joint is made by melting the edges of the parts being joined. And once I melt it, I'm going to have some filler material, and it's added if it's needed. I actually have a 110 volt welding rig at my house here in the garage, and it's amazingly handy for putting stuff together. And I think I'm missing a slide here. Okay, well, let's go on to welding, brazing, and soldering. Soldering. So soldering and brazing are a little different in that they use a non-ferrous metal, right? And if you guys remember from the first week when we talked about materials, non-ferrous is a non-iron based metal with a melting point below that of the base metal. When the filler material has a melting point below 800 degrees Fahrenheit, it is considered soldering. And so if it's a melting point above 800 degrees Fahrenheit, it's considered brazing. When I was younger, the most common material for solder was actually lead. Lead was in there because it has a low melting point, but because lead also happens to be poisonous and has very bad health effects, they've taken the lead out of solder, or have a low concentration of lead in the solder, right? But I used lead solder when I was younger, and it was the most common material because, again, it does have a very low melting point. And I used soldering mainly for electrical work, for joining electrical components. I'm a little old school, and it's funny, I still like a soldered connection. And when I recently installed a stereo in my old car after the factory radio failed, they were pushing using crimped connections. So a crimped connection is basically, it's like a little metal tube, right? And you put the wire in on each side, and then you just squeeze it with a crimping tool, which is a sort of a pliers, but it's shaped to grab it and hold it down. And again, being old school, I actually soldered every connection. And the soldering is more time consuming, but I'm familiar with doing it, and I've been doing it for many, many years. So that's what I did. I ended up soldering stuff. Other place you'll see soldering being used is for making jewelry. Sometimes in repairing jewelry, they'll actually solder. Brazing, I mentioned, is a higher temperature material used as the filler material. So a component that used to be always brazed up until the 1980s used to be actually a bicycle frame. Bicycle frames used to be made by having lugs on the ends, and then you would put the metal tube in the lug and braze it in there. And the reason that this was used as a method was because early on, bicycles were actually considered a serious form of transportation. So many of the roads in the United States were actually built to accommodate bicycles, not cars, because cars weren't around yet. But bicycles were not cheap. They were a significant amount of money. So, and not every place had good roads. So the reason that they were brazed together was that if you had a damaged bicycle tube, metal tube there, you could go to a blacksmith. He would heat up the lug and melt the brazing material. You can take that steel tubing out and then replace it and braze the joint again so that you now had a repaired bicycle. It was not until the 1980s that welded frames became very popular, and now predominantly you will see welded frames. And that also allowed for a lot of different materials that are being used. So I'm going to go back to the welding for a second because I mentioned that I was missing a slide. There are, well, I'll speak about it in here. There are two main classes of welding, and one is arc welding and the other is resistance. Arc welding is something that you may have seen because for some reason in a lot of movies, TV shows, you'll see people arc welding, especially when it comes to construction. I think it's because it kind of looks cool. What it does, it relies on electric arc between an electrode and the metal. And if you've seen it done, there's generally sparks flying. The guy has a shield on, has a face shield that is very dark so that he doesn't go blind looking at those sparks. But it's often used in the field. So if you go through a construction site and they're putting up a steel frame for a building, you'll see arc welding going on. And inside of arc welding, there's different types. So there's the old stick welders, as we call them. And they basically, you have a welding rod and you have a ground and there's an electric current going through there. And as you touch the metal that you're welding with the rod, it completes the circuit. You'll see the sparks, it generates heat, and then that melts, and then the filler material is added. Some of the newer methods are what's called MIG and TIG welding, right? So my welder is actually a MIG welder, and the MIG stands for metal inert gas. And it allows you to use two different types of a wire. It's basically a wire in there. And it either has a flux core in the middle, or you could use a shielding gas, which is what I prefer to use, is a shielding gas. And so the point actually lets that gas come through, and that gas basically shields the weld so dirt doesn't get in while you're welding it, because the most common thing for a weld to fail is actually because there is dirt and it doesn't allow a complete connection in there. So like I said, the inert gas is kind of pumped in through the tip, and that keeps that center clean. You'll also see if you use a flux core welder, there's a little more spattering because that flux that's in there is there to do the same thing, but it'll splatter as you're welding. And the one thing when we do get back to campus, I would say to everybody in this room, please contact me. And one of the things that I have done is I've actually brought this class down to the machine shop and taught people how to weld. We have MIG and we have the TIG. And TIG is a little different because it's actually it's tungsten inert gas welding. So that T is for the tungsten. And again, it's a similar concept to the MIG, but slightly different. And it works very well, and we use them, and I will gladly teach anyone in this room how to do that when we get back on campus, because a um, we do have a welding room in the machine shop, so it's a great place to see that. The other type of welding is resistance welding. And in resistance welding, the parts are butted together and the ends are heated. So because I could be dealing with big parts and I'm butting them together, this is usually a shop process. So I mentioned that arc welding is often used in the field. Resistance welding is generally a shop process and is not used in the field. I also mentioned earlier I have a small 110 volt MIG welder, and honestly, it is like the size, it's like smaller than a carry-on for an airplane. So I have actually thrown it into the trunk of my car and brought it to people who needed to borrow it. So, I could do that, and all I need for that one is 110 volts. The stuff we have in the machine shop is larger, and it's 220 volt. The larger welders will allow us to weld thicker materials. I'm limited with the 110 to how thick a material I could weld, but as long as you work within those parameters, they work very well. So a few weeks ago, we talked about engineering drawings, and one of the things you'll see on the drawings are welding symbols. And basically that's telling you how I'm going to finish the end or ends that I'm welding together. So if you look at this drawing, you'll see various different types, either a bead weld, a fillet weld, or a plug or slot weld. And then you'll see whether it's a groove or a butt, and that is telling you how I'm finishing the sides that are being connected. So in a square, you'll see, and it's just two parallel lines, the symbol for that, I'm basically finishing them off square. And if it's a thin piece of metal, or two thin pieces of metal, I should say, generally I'll just cut them as a square. So in some restoration work, when I'm working on older vehicles, I tend to just use a square ends and then just weld them, because sheet metal is pretty thin, right? But if I'm dealing with a thicker piece of metal, I might end up using either a V, a bevel, or as you look on the rest, a U, J, flare V, or flare bevel. And what this allows, by using like the V or the bevel, it allows me to get in and over several passes weld a much thicker or two much thicker pieces of metal together. So bearings. So we've all probably seen, and we all use bearings, and there's different types of bearings, and I'm going to talk about them. I wish I had, I could pass them around to you guys now, but unfortunately, we're not together. So bearings are used to hold shafts that must rotate relative to a fixed support. The two main groups of bearings are roller bearings and journal bearings. And we'll talk about the difference between the two. So I'm going to start off with roller bearings, and they basically contain an inner race, an outer race, and rolling elements. Examples include ball bearings, straight roller bearings, and tapered roller bearings. So ball bearings, probably the simplest of the bunch. Basically, I have inner race, outer race, and a series of ball bearings in the middle. Now, the picture here shows a ball bearing, and the balls are in a separator, which keeps them evenly spaced. Not all ball bearings have that separator. That's, like I said, there to keep them evenly spaced. You know, years ago, and you guys are tired of me talking about stuff that happened years ago, but when I was growing up, if you went into a hardware store, you could actually buy the loose ball bearings, right? And so if you were repacking a set of bearings on a wheel, on your bike, or whatever, you would actually buy new bearings and take it apart, clean it out, put in the new bearings, pack in the new bearings, and put everything back together again. So that's something, and they're still available. It's just that you gotta look a little harder to find them now. But so the gap, if you look at that picture between the inner and the outer race, there's a gap where you could see the ball bearings in there. Sometimes that could be sealed, and not sealed to keep the dirt out. So in certain applications, you want to make sure that that does not get dirt inside of it, because the dirt will make the bearings wear out much faster, right? So if you hear the term sealed bearings, that's what they mean. That means that there's a seal in there so that dirt will not get in there and damage the races. So the one negative with the ball bearing like this is that there's a very small contact point. It's basically like the tip of the ball is against one race or the other race. So if I have a larger load, I might need a larger area to be in contact. So if I need a larger contact area because I have a larger load, I may have to go to a cylindrical roller bearing instead. So this is a straight roller bearing, and in the picture you could see that instead of balls I have these cylinders. And so what that does is it makes a larger contact area, and if I have a larger contact area, I can carry a greater force without damaging the race or the bearing, right? A variation going on that, because this is a straight roller bearing, is a tapered roller bearing. So a tapered roller bearing also has cylindrical bearings in there, cylindrical little rods in there. And what they are used for is they're used because they can handle both a thrust and a radial force. A radial force is a force going outward, and a ball bearing and a straight roller bearing could both handle a radial force. But if I put a sideways load on that, which is called the thrust load, that bearing will actually fall apart. It'll just push through. So to eliminate that, I have this tapered roller bearing, and if I basically am pushing out on the big part into the thinner part, there's no way that that could come apart, right? So common use of these bearings is in automobile wheel bearings. Use tapered roller bearings. There's generally two of them, one on each side, one pointed one way, one pointed the other, and that way it can handle the thrust load without the bearing coming apart. So I mentioned earlier that there is a difference between roller bearings and journal bearings. So journal bearings do not have rolling elements. The shaft rotates in a sleeve lubricated by oil. The crankshaft in your engine is an example of a journal bearing. Now, you may have heard, and I hope you have, people say, do not rev your engine until it reaches normal operating temperature. Do not go at high RPMs until your engine reaches normal operating temperature. And the reason for that is because, again, these journal bearings are a sleeve lubricated by oil. When your car is cold, the oil is thicker, right? And as such, it doesn't flow perfectly well through the bearing. As the car warms up, then the bearings are well lubricated, and that's why you should not abuse your poor car engine until it reaches operating pressure. And I should say, you shouldn't abuse your car engine no matter what, because you could use it, but please do not abuse that poor car engine. And this is coming from somebody who now has on one of his vehicles 240,000 miles. And if I didn't maintain it properly, I don't think it would have lasted 240,000 miles. So, all right. So gears. Gears is a fun topic. When I was growing up, people that were into cars were called gearheads. If you ever watch the wonderful show on cars from England that I love to watch, especially the older ones, Top Gear, right? We talk about, because cars use gears, right? We have gears in cars. Right? So why do I have gears in cars? Well, gears can be used to increase rotational speed and decrease torque, or to reduce rotational speed and increase torque. That's really the only two reasons that I'm using gears. So I'm either making something go faster, right, by increasing the rotational speed, or I'm actually multiplying the torque, which is making it go slower, right? Only two things I use for gears. So different types of gears that you'll see out there. This is a spur gear, and this is the most common type of gear. If you look at the spur gear, I have the teeth on the outside, and I have a shaft in the middle of it, and the shafts have to be parallel to each other for this to work, right? So you'll also hear something called the effective radius or the pitch radius. So we're going to talk about gear ratios in a little bit, and basically that radius or the number of teeth become important things for us when we're looking at gear ratios. So this is a picture of a rack and pinion. And a rack and pinion, I have the pinion gear and I have the rack, and it converts rotational motion into straight line motion. The device that uses rack and pinion that you're probably most familiar with is automobile steering, right? So most cars today have a steering rack that is rack and pinion. Not all cars did. My older cars do not have rack and pinion. So, but all the newer cars do have that I own have rack and pinion steering in them. But there's another place where rack and pinion is used, and you guys may have used both of these devices that I'm going to mention, but it's also used quite often in the focusing mechanism of either a microscope or a telescope, right? So the next time you're using either a microscope or a telescope, notice that there's probably a rack and pinion that is used for focusing that device. So these are bevel gears, and they're different from the spur gears in that they're formed on a conical surface. And what this allows us to do is to redirect the motion at 90 degrees. So in the spur gears, the shafts have to be parallel, but with the bevel gears, I could do them at 90 degrees. So it allows me to redirect the motion, allows me to build certain other things. The thing that I'm not going to get into in this discussion are differential gears, but I am going to post a video for you guys to see how differential gears work. Um, they're kind of interesting. So helical gears, and they're an alternative to spur gears. Um, if you look at the way the teeth are made, they're at an angle, and then as they mesh together, what this actually has them produce less noise and vibration than spur gears. So one of the places you may see them is if you ever take apart an automatic transmission, they're used inside automatic transmissions. I mentioned that some cars and some older cars did not use rack and pinion for the steering. And one of the reasons that they did not was because that was before cars had power steering. And so some of those actually used a variation on a worm gear. And the worm gear was used where a large gear reduction was needed. So some of them actually used some kind of this type of method for steering because it allowed the steering to be lighter. So gear ratios, very, very important thing. Um, and it's basically will tell me whether I'm doing one of the two things that I said I'm going to be doing. So I'm either going to be increasing the speed or I'm going to be increasing the torque, right? And it's the relationship between the number of teeth in gear 1 to the number of teeth in gear 2. If one gear has 22 teeth and the other has 30, the gear ratio is 0.73. And what that's telling me that for each turn of gear 1, gear 2 is going to rotate 0.73 times. So in this case, I'm decreasing the speed, but I'm increasing the torque. So think about it. If you are trying to start off, you want to increase the torque. You don't want to increase the speed. You want to increase the torque so you could start moving. Or think about it when you're on a bicycle. If you're on a bicycle and you go up a hill, you are going to want to increase your torque, multiply your torque, so you can make it up the hill. So you will go to a smaller gear in the front of your bicycle and a larger gear in the back, and you'll have a less than 1 gear ratio where you'll be pedaling faster than the rear wheel is turning. And then when you get to the top of the hill and you start going down, you will switch to a bigger gear in the front and a smaller gear in the back, and that will end up giving you a ratio where you're decreasing your torque, but you're increasing your speed. So similar to gears are belt and chain drives, right? And belt and chain drives will transfer rotation and torque between shafts. On a belt drive, there can be some slip, right? So this is actually a timing belt on an automobile engine, right? And so the timing belt is keeping the camshaft, which is opening and closing the valves, synchronized with the crankshaft, which is raising the pistons up and down, right? So it uses a belt, and that belt, it could be using a set of gears, and in some cases, like some race cars, they do use gears instead of the belts, right? But the thing with a belt is it deals better with some vibration, right? And a chain and a belt don't have to be perfectly aligned because it will absorb some vibration, like I said. The ratio of a belt or a chain drive is actually similar to the ratio of a gear set. And whereas in the gear set, in the previous slide, I talked about the number of teeth. On a belt or a chain drive, I'm comparing the ratios of the one the one radius to the other radius, and that will tell me if I'm multiplying speed or multiplying torque. So I hope you enjoyed this lesson, and I will be posting some videos also on Blackboard. Please watch them all and contribute in the discussion forum. And if you have any questions, please email me. Thank you.